we were discussing the inclusive education, and we discussed about different social, philosophical, and right-based viewpoints on the education and the need for inclusive education. Now let us g- look a bit into different technologies in this class so that we have a nice balance between technology and the social side. Um, do you know the name of this person? Yes, no,
No, ma'am.
no, anyone?
Oscar Pistorius.
Yes, this is Oscar Pistorius. So actually the name is written. If you see, it is partially written in the picture only. Uh, so Oscar Pistorius actually made quite news headlines. I think 2 Olympics back, because he is a person with disability. He does, as you can see from the picture, he runs with prosthetic legs, and he actually competed not in the Paralympic but in the Olympic Games. As we know, the Olympic Games, which are for the able-bodied people. So just for a trivia, those of you don't know, there is a version of Olympic which is called the Paralympic, which is an Olympic game of persons with disability, and there are various different types of games included, including athletics, footballs, like those which we don't generally think about, even archery, shooting, the javelin throwing, all these games are included in the Paralympic, and Paralympic just happened last year. So it was with Olympic, it was supposed to happen in 2020, but got delayed due to COVID. So in 2021, Paralympic happened, and if you are interested, you can look up to it. Each year they have a different motto, and what is very yeah, also interesting is that actually India um, has won quite a number of medals in Paralympic. But unfortunately, we do not know the names of our para athletes. And anyway, apart from some games like cricket and football, as you can understand, the condition of the players of other games are not very good. Generally, after their career ends, they need to kind of take up all kinds of menial jobs for sustenance, and we know very few names. So the condition of para athletes are even worse. But okay, this is not the discussion today. So I thought that today we will discuss about the human machine interaction. And in the next week classes, we'll try to go deeper into one aspect of the brain computer interaction, because I know it is a long pending, the discussion from our side. So I guess you have heard the term prosthetics, right? We all have more or less heard the term prosthetics. We have seen that people walks with the wooden legs. Then we have heard about Sudha Chandran, the Jaipur feet. These are all the different prosthetics that, in absence or in loss of a biological limb, person, this kind of limb substitutes are used to regain some of the activities, or in this case mainly the mobility of the limb. So nowadays it is actually the era of what is called the intelligent prosthetics, and also the neuroprosthetics. What does intelligent prosthetic means? If you see in the earlier, like the most commonplace prosthetics, actually what you will see in India, these are the wooden prosthetics, or with, if they are very good, they are mechanized prosthetics. So basically, they gives a mechanical action in place of the lost limb, but they really do not have any interface with the body. It is kind of like an external device, or an external you know external thing that you attach to the body, and you can do basic movements with that. But nowadays, what people are trying with the advances in the fields, like the robotics, signal processing, mechatronics, and machine learning, we are coming up with a thing called intelligent prosthetics. So these prosthetics, they actually interface with the body. So the idea is that, just like we can move our muscles, say, take example, say my hand, or your hand. So how do you move your hand? It is not a mechanized movement, right? We control our hand movement through our, like, as per our will, through our brain signals, correct? So that means there is a pathway from our brain neuron to my hand muscles. So that sensory neuron. So what happens if I accidentally touch a hot surface? I quickly retract my arms. So here what happens, a complete pathway is there, right? My sensory neurons near my skin are sensing that the surface is hot. The information is going to my brain via the electrical pulses, and the brain is acting, or in this case, what we call the reflex action. If you recall your class 10 biology, this is the pathway through our spinal cord. Okay, so it is giving a signal that you need to retract the arm. So my actuator muscles, they are retracting my arm. So how can we also do the similar thing with the prosthetics? So this is one of the example, the biome ankle system. This is clinically shown to be the first leg prosthesis to achieve biomechanical and physiological normalization, allowing persons with leg amputation to work with normal levels of speed and metabolism as if their legs were biological once again. Because whenever a person is using prosthetics, and which are, so we are still to go some extent to actually make prosthetics like the our biological limbs, there are some associated overhead. Because of course, if you have a, say, the thing that if you have a the wooden protruding the wooden component attached with your body, then there is you also need to think about how will you move it, how will you adjust your the walking gait. Because you cannot walk with that wooden thing in the same manner, with the same gait that you were doing earlier, right? So, uh, and then what happens to the speed? How do you maintain balance? All these kinds of things. And you may think that I am saying wooden legs, wooden legs. Who uses wooden legs these days? Actually, if you go to the rural areas, I know personally people from Kharagpur who have lost both of his legs and one arm in an accident. He still uses wooden legs, because these the thing is that there is also a cost component and another accessibility component associated with this kind of uh, very updated and sophisticated technologies, right? Another, so that is one of the main challenges that we also discussed, that why we have such low assistive technology penetration, right? So another reason, I like this example of this biomancle because this person, he is an MIT or Harvard professor, and he actually designed, you can see he has lost both of his legs, and he actually designed this biomancle after he lost his leg. And he also spearheads the biomechatronics lab there, and he really does some nice work. So I would like to play this video. This is a bit longer video, but I think you will like it, and it is worth the time. Just give me.
Looking deeply inside nature through the magnifying glass of science, designers extract principles, processes, and materials that are forming the very basis of design methodology. From synthetic constructs that resemble biological materials to computational methods that emulate neural processes, nature is driving design. Design is also driving nature. In realms of genetics, regenerative medicine, and synthetic biology, designers are growing novel technologies not foreseen or anticipated by nature. Bionics explores the interplay between biology and design. As you can see, my legs are bionic. Today, I will tell human stories of bionic integration, how electromechanics attached to the body and implanted inside the body are beginning to bridge the gap between disability and ability, between human limitation and human potential. Bionics has defined my physicality. In 1982, both of my legs were amputated due to tissue damage from frostbite incurred during a mountain climbing accident. At that time, I didn't view my body as broken. I reasoned that a human being can never be broken. Technology is broken. Technology is inadequate. This simple but powerful idea was a call to arms to advance technology for the elimination of my own disability and ultimately to the disability of others. I began by developing specialized limbs that allowed me to return to the vertical world of rock and ice climbing. I quickly realized that the artificial part of my body is malleable, able to take on any form, any function, a blank slate for which to create perhaps structures that could extend beyond biological capability. I made my height adjustable. I could be as short as 5 feet or as tall as I'd like. So when I was feeling badly about myself, insecure, I would jack my height up. But when I was feeling confident and suave, I would knock my height down a notch just to give the competition a chance. Narrow wedge feet allow me to climb steep rock fissures where the human foot cannot penetrate, and spiked feet enabled me to climb vertical ice walls without ever experiencing muscle leg fatigue. Through technological innovation, I returned to my sport stronger and better. Technology had eliminated my disability and allowed me a new climbing prowess. As a young man, I imagined a future world where technology so advanced could rid the world of disability, a world in which neural implants would allow the visually impaired to see, a world in which the paralyzed could walk via body exoskeletons. Sadly, because of deficiencies in technology, disability is rampant in the world. This gentleman is missing 3 limbs. As a testimony to current technology, he is out of the wheelchair, but we need to do a better job in bionics to allow one day full rehabilitation for a person with this level of injury. At the MIT Media Lab, we've established the Center for Extreme Bionics. The mission of the center is to put forth fundamental science and technological capability that will allow the biomechatronic and regenerative repair of humans across a broad range of brain and body disabilities. Today, I'm going to tell you how my legs function, how they work. as a kind of case in point for this center. Now, I made sure to shave my legs last night because I knew I'd be showing them off. Bionics entails the engineering of extreme interfaces. There's 3 extreme interfaces in my bionic limbs: mechanical, how my limbs are attached to my biological body; dynamic, how they move like flesh and bone; and electrical, how they communicate with my nervous system. I'll begin with mechanical interface. In the area of design, we still do not understand how to attach devices to the body mechanically. It's extraordinary to me that in this day and age, one of the most mature, oldest technologies in the human timeline, the shoe, still gives us blisters. How can this be? We have no idea how to attach things to our bodies. This is the beautifully lyrical design work of Professor Neri Oxman at the MIT Media Lab, showing spatially varying exoskeletal impedances, shown here by color variation in this 3D printed model. Imagine a future where clothing is stiff and soft where you need it, when you need it, for optimal support and flexibility without ever causing discomfort. My bionic limbs are attached to my biological body via synthetic skins with stiffness variations that mirror my underlying tissue biomechanics. To achieve that mirroring, we first developed a mathematical model of my biological limb. To that end, we use imaging tools such as MRI to look inside my body to figure out the geometries and locations of various tissues. We also took robotic tools. Here's a 14 actuator circle that goes around the biological limb. The actuators come in, find the surface of the limb, measure its unloaded shape, and then they push on the tissues to measure tissue compliances at each anatomical point. We combine these imaging and robotic data to build a mathematical description of my biological limb, shown on the left. You see a bunch of points or nodes. At each node, there's a color that represents tissue compliance. We then do a mathematical transformation to the design of the synthetic skin, shown on the right. And we've discovered optimality is where the body is stiff, the synthetic skin should be soft. Where the body is soft, the synthetic skin is stiff. And this mirroring occurs across all tissue compliances. With this framework, we produce bionic limbs that are the most comfortable limbs I've ever worn. Clearly, in the future, our clothing, our shoes, our braces, our prostheses will no longer be designed and manufactured using artisan strategies, but rather data-driven quantitative frameworks. In that future, our shoes will no longer give us blisters. We're also embedding sensing and smart materials into the synthetic skins. This is a material developed by SRI International, California. Under electrostatic effect, it changes stiffness. So under 0 voltage, the material is compliant. It's like floppy like paper. Then the button's pushed, the voltage is applied, and it becomes stiff as a board. We embed this material into the synthetic skin that attaches my bionic limb to my biological body. When I walk here, it's no voltage. My interface is soft and compliant. The button's pushed, voltage is applied, and it stiffens, offering me a greater maneuverability of the bionic limb. We're also building exoskeletons. This exoskeleton becomes stiff and soft in just the right areas of the running cycle to protect the biological joints from high impacts and degradation. In the future, we'll all be wearing exoskeletons in such common activities such as running. Next, dynamic interface. How do my bionic limbs move like flesh and bone? In my MIT lab, we've studied how humans with normal physiologies stand, walk, and run. What are the muscles doing, and how are they controlled by the spinal cord? This basic science motivates what we build. We're building bionic ankles, knees, and hips. We're building body parts from the ground up. The bionic limbs that I'm wearing are called biomes. They've been fitted to nearly 1,000 patients, 400 of which have been US wounded soldiers. How does it work? At heel strike under computer control, the system controls stiffness to attenuate the shock of the limb hitting the ground. Then at mid stance, the bionic limb outputs high torques and powers to lift the person into the walking stride, comparable to how muscles work in the calf region. This bionic propulsion is very important clinically to patients. So on the left, you see the bionic device worn by a lady. On the right, a passive device worn by the same lady that fails to emulate normal muscle function, enabling her to do something everyone should be able to do, go up and down their steps at home. Bionics also allows for extraordinary athletic feats. Here's a gentleman running up a rocky pathway. This is Steve Martin, not the comedian, who lost his legs in a bomb blast in Afghanistan. We're also building exoskeletal structures using these same principles that wrap around a biological limb. This gentleman does not have any leg condition, any disability. He has a normal physiology. So these exoskeletons are applying muscle-like torques and powers so that his own muscles need not apply those torques and powers. This is the first exoskeleton in history that actually augments human walking. It significantly reduces metabolic cost. It's so profound in its augmentation that when a normal, healthy person wears the device for 40 minutes and then takes it off, their own biological legs feel ridiculously heavy and awkward. We're beginning the age in which machines attached to our bodies will make us stronger and faster and more efficient. Moving on to electrical interface, how do my bionic limbs communicate with my nervous system? Across my residual limb are electrodes that measure the electrical pulse of my muscles that's communicated to the bionic limb. So when I think about moving my phantom limb, the robot tracks those movement desires. This diagram shows fundamentally how the bionic limb is controlled. So we model the missing biological limb, and we've discovered what reflexes occurred, how the reflexes of the spinal cord are controlling the muscles. And that capability is embedded in the chips of the bionic limb. What we've done then is we modulate the sensitivity of the reflex, the modeled spinal reflex, with the neural signal. So when I relax my muscles in my residual limb, I get very little torque and power. But the more I fire my muscles, the more torque I get, and I can even run. And that was the first demonstration of a running gait under neural command. Feels great. We want to go a step further. We want to actually close the loop between the human and the bionic external limb. We're doing experiments where we're growing nerves, transect nerves through channels or microchannel arrays. On the other side of the channel, the nerve then attaches to cells, skin cells and muscle cells. In the channels of motor channels, we can sense how the person wishes to move. That can be sent out wirelessly to the bionic limb. And then sensors on the bionic limb can be converted to stimulations in adjacent channels, sensory channels. So when this is fully developed and for human use, persons like myself will not only have synthetic limbs that move like flesh and bone, but actually feel like flesh and bone. This video shows Lisa Millette shortly after being fitted with 2 bionic limbs. Indeed, bionics is making a profound difference in people's lives.
Oh my God, I can't believe it. It's just like I've got a real leg. Now don't start running.
Now turn around and do the same thing walking up. Walk up, get on your heel to toe, like you would normally just walk on level ground. Try to walk right up the hill.
Oh my God.
They're pushing you up?
Yes, I'm not even, I can't even describe it.
It's pushing you right up.
Next week, I'm visiting the centers. Thank you. Thank you. Thank you. Next week, I'm visiting the Center for Medicare and Medicaid Services, and I'm going to try to convince CMS to grant appropriate code language and pricing so this technology can be made available to the patients that need it. Thank you. It's not well appreciated, but over half of the world's population suffers from some form of cognitive, emotional, sensory, or motor condition. And because of poor technology, too often conditions result in disability and a poor quality of life. Basic levels of physiological function should be a part of our human rights. Every person should have the right to live life without disability if they so choose. The right to live life without severe depression. The right to see a loved one in the case of seeing impaired. Or the right to walk or to dance. in the case of limb paralysis or limb amputation. As a society, we can achieve these human rights if we accept the proposition that humans are not disabled. A person can never be broken. Our built environment, our technologies are broken and disabled. We, the people, need not accept our limitations, but can transcend disability through technological innovation. Indeed, through fundamental advances in bionics in this century, set the technological foundation for an enhanced human experience, and we will end disability. I'd like to finish up with one more story, a beautiful story, the story of Adrienne Haslet Davis. Adrienne lost her left leg in the Boston terrorist attack. I met Adrienne when this photo was taken at Spaulding Rehabilitation Hospital. Adrienne is a dancer, a ballroom dancer. Adrienne breathes and lives dance. It is her expression, it is her art form. Naturally, when she lost her limb in the Boston terrorist attack, she wanted to return to the dance floor. After meeting her and driving home in my car, I thought, I'm an MIT professor. I have resources. Let's build her a bionic limb to enable her to go back to her life of dance. Brought in MIT scientists with expertise in prosthetics, robotics, machine learning, and biomechanics. And over a 200-day research period, we studied dance. We brought in dancers with biological limbs, and we studied how do they move? What forces do they apply on the dance floor? And we took those data and we put forth fundamental principles of dance, reflexive dance capability, and we embedded that intelligence into the bionic limb. Bionics is not only about making people stronger and faster. Our expression, our humanity can be embedded into electromechanics. It was 3.5 seconds between the bomb blasts and the Boston terrorist attack. And 3.5 seconds, the criminals and cowards took Adrienne off the dance floor. In 200 days, we put her back. We will not be intimidated, brought down, diminished, conquered, or stopped by acts of violence. Ladies and gentlemen, please allow me to introduce Adrienne Haslet Davis, her first performance since the attack. She's dancing with Christian Leitner.
Ring my bell, 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 ring my bell. Sometimes you love it, sometimes you don't. Sometimes you need it, then you don't, then you let go. Sometimes we rush it, sometimes we fall. It doesn't matter, baby, we can take it real slow.
Okay, so I guess you have enjoyed the talk. Actually, Professor here described the work of the bionic limbs very beautifully, and I thought that it would be better to hear him talk because he will definitely describe it more interestingly and accurately than I could have done. So. I know that a lot of you are interested in robotics. Lots of you are interested in the mechatronics. So it will be really nice to some initiatives like this to came out of our IIT KGP, and my knowledge may be a bit backdated, and if you know that we have this kind of initiatives or some developments and you would like to share with us with the class, please feel free to do so. And I know we also invite, like not we, the students, you have different clubs and you also invite lots of eminent professor for different talks. So you may also like to invite professors like how the professor here, who can really show the others like how technology can contribute, how latest cutting edge, bleeding edge, whatever you would like to call, can contribute to make the world a better place for living. So let us move on. Please don't ask me any question from it because, of course, I do not have in-depth knowledge on his research work as of yet. Okay, so now what we are moving towards is it is termed as the human-centered cognitive orthosis. So like prosthetics and orthotics. So orthotics is like, as you can understand, for mainly the mobility and the movement part. Uh, and the cognitive, because now not only we are seeing the to regain limb movement, but also how the movements can be as naturalized, like if I can use the word naturalized, and as we will do with our biological limbs. So our cognitive functions are also, and there are things which are the burning the neurons, which are actually replacing, which can actually replace the damaged biological neurons. So just from the external limbs, we are now also moving towards the cognitive implants, brain implants, actually neuronal implants, um, this kind of things. So, what does human machine interactions entails? Of course, signal processing. So, in this slide, I have only included the EMG because I was developing as a part of if someone has lost one of their biological limbs or the muscle power. So, the EMG, just like the EEG you may have heard, uh, which captures the brain signal, is the ECG, what we do in the hospital regularly, which is the cardiogram, which captures the cardiac signal or the heart signals. So similarly, the EMG captures the signals, the electrical signals from the muscles. So it involves signal processing, of course, machine learning and artificial intelligence, and brain computer interfaces techniques. So how do we do the like how sig- signal processing of the EMG occurs? So the full form of the EMG is electromyography, just like ECG is electrocardiogram. So like this. So what happens? I think if you have seen in the picture that when recording the brain signals, lots of white color, the electrodes are placed on the scalp or on the head, right? Or when you go to do an ECG in the hospitals, there are the electrodes which are placed on your at different positions on your chest, and also some at your ankle part to collect the heartbeat movements. So similarly for the EMG, what we do is the electrodes, these multi-channel, the electrodes are placed on the muscles, like on the limb muscles. Okay. So it records these signals from the EMG, and this signal is filtered. It kind of discretized, because from continuous signals we identify discrete features. I think in signal processing, you have read about, those of you who have taken signal processing or know about it, you have read about the different transformations which kind of which can discretize, like from a continuous signals can come up with discrete features. Then these features we like in machine learning, we give the features an input to the classifier, and this classifier kind of with the repeated training of the classifier, we understand that how a particular signal corresponds to a particular movement. Now, as you have seen in the previous video, what happens first, this training, of course we cannot train it on the person who is already using an artificial limb. We train it on a person with the biological limb so that we can establish this classifier or correlation. So it is basically, like we have a ground truth, that person with biological limb, when this is their the EMG reading, then my classifier learns that this is the movement that they need to do. In this case, it is the speed control, like from open palm to this movement with the index and the thumb. So it learns that this is the output that is required. Then when it comes to a person who is wearing the limb or the orthotics, it from the person, now you can think it like as a test data, that it records the EMG, and from its knowledge from the trained model, the electronic controller understand what kind of speed it should take or how to control the speed. Okay. So what happens when we take a raw signal, the signal, just give me a moment. When the sorry, by this multi-channel the electrode, the raw AMG signals are recorded. Now, if you have seen the ECG readings, or like the any kind of signal reading, you will know that basically raw signal looks like this. So it's kind of ups and down, the wavelength and the frequency and things like that. So what happens? It is classified into different windows or the classification epochs. So the window length is L. So EMG windowing in continuous feature extraction. So this is successive window length L. The ACMG data for classification is divided into C segments for each and every L, that is the length of the integrated sample as a feature extraction, and the start point is shifted every S. So, okay, let me rephrase it. What happens is that at each step, instead of taking the whole signal at the same time, I know that those of you have a background in signal processing, you will know better and you can understand it better. And this is just a very rough explanation for those who don't have. And please correct me if you think at some point I may term a bit ambiguous or inaccurate. So this continuous raw signal is classified into different window sizes, lengths, which basically serve as an epoch. And each of these window size, what we do, we shift the start point at is after a particular predetermined length at a continuous interval. So, and with these particular segments, we convert this this window to a continuous set of features to denote this raw signal. Because in my machine learning model, I cannot give input a continuous signal like this. I need to give input of some numerical features that describes a part of the signal. So now there are two operations which are generally done. Either the machine learning model is classification or regression. So what happen in classification? Say I want to do 4 basic operations. This is my the EMG the electrode placements, and from the 4 limb I want to do open, close, up and down. Okay, pronation and supination. So from the we capture data from the electrodes, the EMG data, and for each of these movement we record how the signal activity is happening, and then we train a machine learning classifier from the on the extracted features from the signal. Now there is a problem. Say when we actually move our hand, we do not do this kind of distinct operation. So there is also continuous movement involving from when we do an open to close or close to open, or when we are swinging our arms, right? Or like sorry, swinging our palm in this case. So for that, there is another type of modeling, which is the regression. What regression does is that instead of classifying the motion that it is either open or closed, like to discrete motions, it estimates the continuous movement. Like you can see these are 4 distinct lines for classification. For regression, this is a continuous the estimation that okay, at this part my hand is open, and this is a transition from open to close, and now my hand is closed. Okay. So it is a decision in case of classification, it is a decision, and in case of regression, it is a simultaneous estimation that from open to close or close to open. Now both of them have their importance. Say if you want to detect at which stage my arm is or my palm is, then you need the classification. And if you want to detect that from open I want to go to close, then you need to regression. You need the regression model. So there is another thing involved, which is there is another paradigm which is called the targeted muscle reinnervation, or TMR. As the name suggests, reinnervations means that to reactivate the nerves of some of the muscles. So what happens? Say for example, in this case, say I have lost only my forelimb part. Then this AMG thing, or say I have lost my palm, then this AMG thing and it works. But what happens if I have lost my whole limb, the whole hand, from say the from shoulder up? So then basically how do I control hand movement? By this set of muscles, like this pectoralis major muscles in our chest. So then what happens? This is called innervation because my nerves are not there. So what is done here is that these nerves, these are actually the EMG, the electrodes are placed on these nerves, and these from the activities of these nerves, it is sensed that whether I want to move my hand or not. So you can place your hand on your say the right side of your chest, and you move your hand, and you can see that with your right hand movement actually your chest muscles are also moving. Okay, so from the EMG of the chest muscle through this microprocessor unit. So basically, the microprocessor is doing the signal processing, and the machine learning model, whatever is this there, and then this whole prosthetic is moving. Okay, so this is called myoelectric prosthetic. So myo means muscles, and electric means we are using the electrical signal processing. Okay. So in this way, if someone loses a whole hand, this TMR through this TMR method, this movement is possible in case of the whole hand movement. Okay, but there are some challenges in this technology. First of all, we are doing actually um, in um, as the underlying basis, we are doing signal processing, right? So like any other signal, there are also noises in the EMG signal, because see what we are doing some assumption. See, when you are doing your, see, when you open your palm and close your palm, it is not that only those muscle signals which are involved with the open palm and the closed palms are involved. There are other signals as well. Other small, however smaller movement might be, it will generate a signal spike, right? And of course, and there is no discrete signal saying that okay, this is the particular signal for opening my fingers. No, right? So there are always noise involved in the EMG signal. Then we are measuring the signal with some electronics equipment. So there is an inherent noise there. Then there will be some ambient noise in the signal processing in the environment that you are doing. Then the signal is also inherently unstable. As I have said, like the signal is, it is not that always the same type of signal with the same wavelength, same frequency, same magnitude, same intensity is generated. Then the ECG artifact. So our heart is the most important, electric component in our body. So that signals interferes, and the crosstalk is that in our body for different movements, all the electrical signals are taking place. They are taking place at the same time. So there will be some interference among them. So for these challenges, the work is not as trivial as it seems. So now what happens if I lose my dexterity altogether? So then we have something called the neuromuscular microimplants, which are called the bionic neurons. Bionic neurons. So say if you take the example case for persons with cerebral palsy, so all in this example, we are relying on the fact that my movement, my lip movements are voluntary. That only when my brain will think, it will move the index finger of my left hand, the index finger will move. So that means my brain muscle pathway is still intact. I have lost the muscle, but the other component of the path is intact. Now, what happens is persons with cerebral palsy or in case of paralysis, this brain to muscle pathway is actually it is affected. So there are lots of involuntary movements in persons with cerebral palsy, which is also a challenge in case of developing say exoskeletons or bionic limbs for persons with cerebral palsy, because the movement itself is the involuntary. There is the loss of dexterity, that even if I think I want to move my index finger, I cannot do that. Or even if I don't want to move my left hand, it rocks automatically or it trembles automatically, like in spasticity. So these neuromuscular microimplants, as you can understand, these are the invasive implants. So these are called the bionic neurons. So when the actual biological neurons are damaged, these bionic neurons or implants, they help. So they perform a technique called functional electrical simulation. What it does, it uses electrical currents to activate nerves by innervating extremities affected by paralysis. So one example is this. So it is innervating the extremities which are affected, but in case of the people who do not have dexterity. And then we have the brain computer interfaces or the neurochip, which can create an artificial motor pathway. So this is an example of ankle functional electrical um, simulator, which uses an electrical simulation of the peroneal or the fibular nerve to activate dorsiflexus during the toe up to initial contact period, that is the swing phase. Or let me put it in more layperson terms. So basically, as you can see, there are two implant and one controller here. So when we walk, the very simple gait from the walking, what happens? It requires that we will be able to from the resting foot through electrical simulation, we will be able to lift our heel and the and then from the calf we can understand my only the toe is in contact and my entire foot is lifted. Then I will lift up the leg together, take the leg in front, the swing action, and put the heel down first, and then put the rest of the feet down. So if you recall in biology, when we have studied movement in the human movement, like in class 10 or 9 or 10, it was described like this, that how do we do human movement? First our brain says that, okay, let's do it. Then we lift up the heel. After we lift up the heel and the toe is in touch, we lift up our whole leg and we take the leg forward, then we put the heel down first and the rest of the feet down. Only in this case we are using a bionic neuron and the technology of functional electrical stimulation. So there is a heel switch. So when the foot is resting, when we are in a standing position, there is an electrical simulation. So the foot starts rising. Switch detects that the foot is rising and to the electrodes on the calf, and then the calf muscle lifts the foot accordingly and do not drag. It is very important. In lots of artificial movement, the feet actually drags, but the calf muscle contracts. How will you lift your leg? By contracting the calf muscle, and then as the left is off the ground, the swing motion happens by this hip switch. Okay, and then when the heel touch the ground, then the calf muscle relaxes and it is the ground simulation is switched up until the whole heel is placed on the ground. So as you can see, it requires understanding of biology, the nooks and crannies of human movement. That's why these lots of biological terms, and it requires understanding of like mechatronics, and it also requires this signal processing, of course, and training how to do it. And of course, there are also lots of other the nuances involved, but very broadly, these are the components. So I will stop here today. Any question?
Excuse me, ma'am. Where's the assignment uploaded?
I will upload it today. As I have said, last night I couldn't do it.
Okay. Fine. Thank you.
Okay. Okay, thank you. Do you even listen to the class, most of you?